Yep, comes on everyone. Let's start off. Great. So last thing that we did was conduction. Yeah, now I can see you. So the next thing is radiation. So like I discussed last time, what is conduction, convection, and radiation? So conduction, primarily the heat flows due to the molecular collisions, the energy transfers because of collisions. Whereas in radiation, the energy is transferred due to the photons. So basically there is no movement of matter, you don't need any material for this to transfer. So the question comes like this, exactly what is this radiation? So now we need to use a statement. Do you guys remember this in atomic structure chemistry? What is the drawback of Rutherford model? Anyone remember the drawback of the Rutherford model? There's a statement, according to classical theory of electromagnetism, an accelerating charged particle emits photons. An electron going in a circle has a centripetal acceleration. Therefore, it must emit photons. And if it emits photons, it will lose energy. And when it loses energy, eventually it will collapse into the nucleus. But we observe the nucleuses are stable. Then Bohr comes and gives a statement. There are some specific orbits called, stationary orbits. If you go in these orbits, you are safe, you don't lose energy. That is how he postulates. Now, in that, the statement we are interested is this one. According to classical theory of electromagnetism. So basically, this theory, right, is based on this way. Meaning, think of like this. So whenever the molecules collide with each other, some of the energy is absorbed by the electrons. So the electrons excite to higher orbits. And when they de-excite to lower orbits, they emit photons. Does that make sense? So when photons are colliding with each other, when molecules are colliding with each other, right, the energy, some of the energy is absorbed by the electrons. Electrons will excite to higher orbits from the ground level. And when they de-excite, you get photons. Meaning one simple reason why you can see a flame. Again, what is fire? When you say fire, what is fire exactly? What is fire? Ever thought about it? Fire is nothing but highly heated gas, isn't it? When a gas is heated to a certain temperature, right, the molecules are colliding with each other so rapidly, or they're colliding with such a high energy, the electrons excite to higher orbits, and when they de-excite, you get colors. And so on logically. Uh, if the flame is, little less heat, you will see a red color. If the flame is hot, what color you will see? Blue. A blue flame is more hot than a red flame or an yellow flame. So the order will be like this: red, yellow, and blue. So out of all, the blue flame is the hottest. Simple reason. Blue ka photons have more energy, isn't it? That means to produce a high energy photon, you should collide more rapidly or more strongly. That means you should have more energy, means you should have more temperature. Does that make sense? So the stronger you collide, the more energy you lose. The more energy you lose, the higher the electron can excite. Higher the electron can excite, more energetic photons you get. And best example is this. When you go to the kitchen, switch on the stove and look at the flame. You will observe when the flame is coming out, initially the starting part of the flame is blue. As the flame goes away a little higher, you will see, the color becomes yellowish. Can you visualize that? Next time observe this. Basically, as the flame goes away from the stove, it cools down. The gas cools down a bit, isn't it? The gas is going away from it. It cools down a bit. Once it cools down, temperature decreases, so color goes from blue to yellow. You can see this thing in welding also. When the welding torch is switched on, initially you'll see a blue flame, right? So kind of that's what your classical theory is. Meaning, I kept it in a very simple terms. So basically, when molecules collide, the energy is absorbed by the electrons. Electrons go to higher orbits when they're d-excited, get photons. So that is how we can put it simply. So stronger they collide, more energetic photons you get. So according to classical theory of electromagnetism and accelerating, so that is one way to explain. But this thing goes even beyond that. It says if you just take one particle and accelerate it, you get photons, meaning without any collisions. So now we'll not get into that stuff. It goes beyond. Accelerating charged particle emits photons. But for us understanding, I think the thing which I tell you, that gives you a little idea. This is right. It's also called as Bremsstrahlung radiation. It's a German scientist name, but to keep it simple, we can also call it braking radiation. So from this statement, what we get, if you take any body, so next time when someone asks you what is fire, that is the meaning of it. It's a highly heated gas. So fire has momentum because it has mass. So any body with a temperature greater than 0 Kelvin, the molecules have some kinetic energy. The molecules are in a state of constant vibration. The kinetic energy is 3/2 kT. This is a translational kinetic energy. So when they vibrate or collide, so if you're taking a gas, the molecules collide with each other. If you take a solid, the molecules vibrate, depending on the type of material. Their velocity changes, so they accelerate. Think about it. When you say vibrate, if you go front and come back, didn't your velocity direction change? Vi cap became minus Vi cap. Velocity direction changed. That means velocity changed. That means there is an acceleration. They accelerate. And so photons are emitted. So we'll not go too much into why the photon is coming and all. We will accept that fact and then we will go ahead with this. This process is called radiation. So whenever a body radiates, eventually it will lose energy and cool down. So in radiation, there is no transfer of matter. Best example is your sun. The distance from sun to earth is almost 15 crore kilometers. But even when you go out into the sun right now and put your hand in that sunlight, it feels warm. So you are getting that energy in the form of photons. In radiation, there is no transfer of material and does not require even medium. To propagate. And then all vibrations need acceleration, all bodies should radiate. Yep, all bodies radiate energy.
So won't they just
So, what?
so won't they just keep radiating till the temperature becomes zero?
Okay. So they don't absorb according to you. They'll just keep radiating. Hmm? Clear with this thing. Next thing. So that means according to if you take you and put you in a big furnace, you won't have any problem. I can put you in a 1,000-degree room and burn you. You'll be fine because you'll cool down eventually, right? You absorb also, right? We are only talking about one side of the story, the other side. So if you take a body and the temperature of the body is some, let's say some T. So you start getting all kind of photons. This is again another thing. You don't get any. There is nothing like guarantee like you'll get a single wavelength. You can get all weird wavelengths. We will discuss about that also later on. So we will talk a little about this thing. So this energy of these photons. I'm sure you studied this in chemistry. Is given by hc by lambda or h into frequency. H is your Planck's constant. Whose value is 6.6 into 10 power minus 34 joule second. C is the speed of light. 3 into 10 power 8 meters per second in vacuum. Lambda is wavelength. F is your frequency. And we also know the relation C is equal to F lambda. Now, photons, even though they don't have any mass, but they have momentum. Study de Broglie wavelength. So photons do not have mass, but they have momentum. Basically, photons, right? You can't apply your regular mechanics. This momentum is m into v. All this stuff are not applicable. They have a different equations and different stuff. So when you actually go with speed of light, things are pretty weird. So photons are massless, but have momentum. We will discuss a bit about that again in a chapter called Modern Physics. Massless, but have momentum. That means when you actually shine light onto a surface, it is actually exerting pressure on you. But the problem, it is so small, you don't even feel it. So momentum of a photon is given by h by lambda. Now, other than this, certain terminologies also should know. When we say intensity, intensity is nothing but power by area. Which area? Area in which the energy transfers. Area in which power propagates. Now, for power also can be written as number of photons per second into energy of each photon. Think about it. If you take the number of photons into energy of each photon, won't you get the total energy? And total energy per second is power. So when you say power of something, it's like number of photons per second into energy of a photon. So we can also write power is equal to this number of photons per second into energy is h into f. So from here we can say I is proportional to n into f. Quite a useful result, but we will discuss this again in modern physics in more detail. So intensity of any light source depends on how many photons you're giving per second and the frequency of the photons. So frequency is proportional to energy. I'll just write n per second into f. So these are few terminologies you should know. This right hand side is full of chemistry part that I'm sure at least you know. This energy part I'm sure you know. Momentum, if you don't know, you should remember this. These are important. Clear? Next thing. Now, we define few things. First thing is coefficient of absorption. Let's define like this. The symbol is A. So it's a ratio. So A is nothing but the energy absorbed by a surface by energy incident on a surface. That means if 100 joules of energy falls on the surface and if only 50 joules is absorbed, then A is half. So basically it tells you how much energy is absorbed by the surface. So here we have a special case called black bodies. So for black bodies, A is equal to 1, meaning they absorb all the radiations incident on them. Now, when I say black body, right, people start imagining a black hole. Black hole is a black body, but that would be like a very special case. It's like saying when I say I'm in army, it doesn't mean everyone is a general, right? Maybe someone is an army cook also, right? Or maybe someone is in logistics. So things like that. So when you say you're in Air Force, it doesn't mean everyone is Air Force pilot. There are barely like what 2,000 pilots or 5,000 pilots. But if you see the total Air Force strength, it is almost more than 2 to 3 lakhs. Right? So some of them play other important roles. So for black bodies, A is equal to 1, they absorb all the radiations on it. So just to give an example, a black body need not be black and need not be a body. That is interesting thing about it. So if you go with the word, right, you will be stuck with the problem. So you should just understand what it means and don't go with the word. So for example, sun is close to a black body. Again, that's what I'm saying. When you hear the word black, you think it should be black. Again, understand the definition. What does it say? It simply says whatever falls on the body gets absorbed. Did I ever say you can't emit your own light? So absorb all the energy, make it yours, and then you emit your own light. You don't reflect the light. I hope you're getting the difference. There is a catch. I don't want you to bounce off the light rays. Whatever falls on you, absorb everything, make it your own, and then you emit your own photons. That is completely acceptable. But a black body cannot reflect light. If something falls on you, you can't bounce off the light rays. So sun is close to a black body. Whatever falls on the sun gets absorbed. And then sun emits its own light. For example, moon is not a black body. Moon is a good reflector. So it reflects the sun light onto you. So whenever you think about that, remember sun is close to a black body, right? So a black body can have its own emission. So someone asks you, what's a black body? Simple definition. Whatever falls on it, you should absorb. Should it be dark? Not necessary. You can emit your own light. You just don't reflect. You don't reflect. You don't let anything pass through you. Can have its own emission. So what do you mean by need not be a body? So for that, the example is something called a Ferri's black body. This will be in your boards also. They'll ask you describe a Ferri's black body and draw the diagram and blah blah stuff. So a Ferri's black body is actually a double shelled structure. So here we have a hole. So what happens here is this is the hole here. So if you send a light ray through this hole, this light ray goes and hits this surface, which is slightly inclined. So it bounces off. It bounces off. It bounces off. It keeps on bouncing forever. It doesn't come out. So again, now see, what is the definition of a black body? Anything that falls on the black body must be absorbed. So here the hole, any light ray that falls on the hole will never come back. Making sense? So the hole here behaves like a black body. The hole behaves like a black body. Because what is the definition? See, and thing is, you don't know what is a hole, right? If you're seeing from very far, don't you just think it's just a black thing there? So whatever falls on the hole doesn't come back. So hole is a black body here. That's what I mean by a black body need not be black and need not be a body. So the shell is not the black body. That hole is a black body. Yeah. Negligible. That's why they put this surface coated with lamp black and all. Maybe a little light ray do escape. So there is nothing like 100%. You always get as close as possible. Clear, everyone. So how does this black body look like? Now, the closest thing that we have to a black body is humans made it. There's something called Venta Black 2, if you ever heard about it. So I think almost a decade back, the first time they created this Venta Black 1, it absorbs almost 99.9% of the light. And then I think last 5-6 years back, they created the new one, Venta Black 2. This absorbs 99.9997% or something. It's pretty huge. Quite expensive. So basically, it is made of carbon nanotubes. You know the 660 Buckminster fullerenes? So carbon ka the other form. So these things, right, are made of carbon nanotubes. So when the light ray falls into this carbon nanotube, it gets bouncing inside, it gets absorbed. So the entire structure, right, Venta Black, is actually a carbon nanotubes. So it absorbs all the light. Quite expensive, but we have a cheaper version, not Venta Black. It's called Muso Black. You can get it on Amazon. India mein nahi milega, US mein. I think last time I tried seeing it, it was like almost 8,000 rupees for a 100-gram bottle. And it was actually 4,000 rupees. Remaining 4,000 is customs tax. That is close to thing. So this is how the Musa Black looks. So this.
Hey everyone, today I'm going to be showing you the blackest paint called Muso Black. It absorbs over 99.2% of visible light.
Are you able to hear the audio? No.
So I'm going to be painting some stuff with Muso Black and comparing it
No, audio is clear, right? Okay. So
to Black 3.0 and Singularity. And then I'm going to be painting an entire room with Muso Black and putting a light bulb in it and seeing what happens. Well, actually not an entire room in it. Instructions for how to use the paint using this.
So we're going to paint an apple with the Muso Black.
Cool. That is so cool looking. Looks like I don't even need multiple coats on it. Well, because it's still wet. Now you can still see the contours of it pretty well because it's still wet. So it's glossy a little bit, but let's see what it looks like when it dries. Okay, here we go. Here's an apple painted with Muso Black. This is amazing.
Can you see how it looks? You can't see the depth. It just looks like flat. There is nothing there. It looks a little weird, right? So thing is, normally when you see something, right, you can see the depth, the width, the breadth and height, and here there's nothing because nothing is getting reflected. You just don't know.
Look how it just disappears. You can't even tell what I'm holding. You can't see any contours of it whatsoever. So cool.
Look at this thing. So he kept a black background and he kept this thing. Can you see? On the left side, it looks like there's nothing. So YouTube mein na search this Muso Black karke. There is a guy who made a video on this. He painted a full dress with Muso Black, like a ninja dress. He goes and stands in front of a black wall. You can't see him. Matlab, he gets mixed up. When he opens the eyes, you'll see 2 eyes on the wall. So
That's so cool.
This is a nice thing, see.
Look at this from all angles here. That is the coolest thing I've ever seen. Okay, this is my favorite thing I've ever painted. This is so cool.
Can you see how it looks? It looks like someone just cut the apple in half and they painted black. Na? It just looks like a plain surface. It's actually a 3D thing. You can't see any depth or anything here. So that's how a black body looks like. You can't see. It absorbs everything. Because see, it is not emitting its own light. If this can emit its own light, that's a different story. So black body, an apple is not an emitter. It doesn't have its own light. Now, imagine this situation. Imagine the room you're sitting is painted with Musa black, right? And just switch off all the lights. And if you switch, shine the torch. If you take a torch and switch it on, what do you see? Can you see the walls? You can't see the walls, isn't it? Normally, when you switch off everything in the room and switch only one light, the room is still illuminated, right? The reason the light falls on the wall and gets reflected to you, so you know there is a wall there. But if everything is painted black, nothing comes back, everything gets absorbed. You can't even tell there is a wall. You don't know how big is the room. You don't know the size of the room. And the room looks pretty weird. Matlab, and if you just switch on the bulb, right, you can just see the bulb. You can't even see bulb ka side mein wall, nothing. It just feels like there is something in the sky. So he does something like that.
So this to try.
I'll post this video in the group. You can see it in more detail. So this guy
What
took a
will it
box
look
instead
like
of a
on the
room.
walls in there?
And Musablog is expensive, so he's just painting the whole box with Musa black.
Okay, so I have my flashlight on, and I'm going to be putting it in the box and looking what it looks like.
Now, logically, socho na, if you have a completely closed room and if you put a flashlight like this, you can even try in your room. If you switch on this light, you can still see the whole room gets bright, right? But look at this room.
Like through a small hole. This is so weird. It looks like I'm shining this outside and that's the moon in the sky or something. It's completely black. It's reminiscent of the night sky. You can't see any contours of the box whatsoever.
Dekha, walls kuch nahi dekh rahe andar, even if there's a light. In your room, if you just switch on your flashlight, right, this cell phone guy, you can still see the walls and ceiling. This is how the room looks if you paint everything with Musa black. So if you actually wear a Musa black dress and start running on the roads in the night, cars will just hit you. Don't do that. Pretty bad idea, right? Even if someone sees you, it looks like some dark figure is moving in the thing. So yeah, either you will create a ghost story or someone will just hit you with a car and go.
So cool.
Either way, a bad idea.
Okay, the camera.
He kept the camera inside. You see, other than that light, you can't see anything. And that green thing is a camera reflection. So this is how it looks. It looks like there is a moon or some star in the sky. So this is actually how it looks when you go and stand on the moon and look at the sun. This is how sun looks. Because moon has no atmosphere, right? So there is no dispersion and all. So you don't see the sky. You don't have anything. So think of like this. If you're standing on moon and looking at the sun, this is how it looks. Or if you're standing on moon and someone switches on a light, this is how it looks. If there's no atmosphere, there's no dispersion. It just looks dark.
Is inside there with the light bulb. It looks like the moon out a window or something.
So there, it's an interesting thing. So that's the closest and the cheapest you can make at home, Musa black. Right, you can order from Amazon. They will charge you something, and then they'll get it stuck at customs. Then they'll send you a mail, and then they'll ask you to write a mail saying that you're not going to use this for any terrorist purposes or evil purposes. And then, if you're lucky, they will release it. That is a problem with the customs. So yeah. So there. So a black body need not be black and need not be a body. No. So whenever radiation falls on a surface, three things happen. So if you are sending this radiation, so one, you can get reflected. You can get absorbed. Or you can just pass through. You can get transmitted. Anything else can happen. You reflect, you absorb, or you just pass through. So that means the total energy which you're sending, so Q is the total heat, radiation, or whatever, will go into Q absorption, Q reflection, Q transmission. So you can classify like this. So these are the three things that can happen whenever a radiation falls on a surface. So this is Q absorption by Q. This is Q reflection by Q. So divide the whole thing by Q. Q transmission by Q. This becomes 1. This is A. This is R. This is T. So A is your coefficient of absorption. So if A is equal to 1, remaining towards 0, it's a black body. It absorbs everything. R is your coefficient of reflection. What is R is equal to 1 meaning? Everything gets reflected. It's a perfect mirror, isn't it? So R is equal to 1 is a perfect mirror. T is coefficient of transmission. What do you mean by T is equal to 1? What is T is equal to 1? Everything passes through. Like example, the air in front of you. Can you see air? Everything just passes through. Whatever light is coming, some gets absorbed, but yeah, most of it passes through. This is a transparent substance. So air is there in front of you. Most of the light passes through it. Clear with this? Now we have few definitions. Spectral energy density. So the word spectral meaning spectrum. Getting it? So wavelength, you must have seen this thing. Emission spectrum, absorption spectrum, characteristic spectrum. So when you say spectral, you're talking in terms of wavelength. We will discuss about this also in detail later on. So spectral energy density, which is E lambda. So what it simply means is, this is the amount of energy emitted per second in per unit wavelength. What do you mean by that? See, whenever a body emits light, do you think it emits only single wavelength? It emits multiple wavelengths, right? So each wavelength will contribute, right, some amount of different amounts of energy. Let me give an example. Let's say you have some money with you. Let's say you have 1 rupee coins, 100. Let's say you have 2 rupee coins, 200. And let's say you have 5 rupee coins, 300. And let's say you have 10 rupee coins, 200. Now, if I ask you this question, how much money is 1 rupee contributing to you? 1 into 100, 100 rupees, no? So this is the spectral energy of 1 rupee coins. So here the 1 rupee, 2 rupee, 5 rupee, 10 rupee are like different photons. This is like wavelength. And this is like your A lambda. If I ask you how much is 2 rupees contributing, 400 rupees. How much is 5 rupees contributing? 1500 rupees. How much is this contributing? 2000 rupees. Is that making sense? What is the total money you have? Add all of them. This is the total money you have. 100, 400, 1500, 2000, 2000. But in that, the spectral energy density is per unit wavelength. So your body is emitting energy in different wavelengths. For example, let's say 1 angstrom, 1000 angstroms, 2000 angstroms, 5000 angstroms, and 10,000 angstroms. Is that making sense? So each wavelength is contributing a certain amount of energy. So that is called as spectral energy density. Is this analogy making sense? So you have money with you, but in that 1 rupee coins, 2 rupee coins, 5 rupee coins, and 10 rupees coins are contributing different amounts of money. Is that making sense, everyone? Sure. So whenever you hear the word spectral energy density, right, it simply means the contribution of each wavelength in the total energy. So think of money. That would be a good example. It makes more things clear. So energy is like money, right? And spectral energy density is like the money in each denomination. I hope that's making sense. And then we define something called, but again, we will discuss that. We have Wien's displacement law, something that we will see it again. Then we have something called emissive power. It's the amount of energy emitted per second per unit area. In the form of radiation. This is actually same as intensity. Intensity is that only energy per second per unit area or power by area. And there are just few definitions. And then we have Kirchhoff's law of radiation. So what this thing says is, at a given temperature, the ratio of spectral emissive power, that's your E lambda, to spectral absorptive power. So spectral meaning at a given wavelength. A lambda is constant. It looks little thing, but let me tell you in simple words. So what this thing is saying is the amount of energy you emit at a given wavelength to the ratio of this is constant. So what this simply means is E lambda is proportional to A lambda. So what this thing is saying is, if you are a good absorber, means if you absorb good, then you also emit good, isn't it? So this Kirchhoff's law of radiation simply what it tells us, a good absorber is also a good emitter, and vice versa. Think about it. If you have a good absorber but a bad emitter, what happens? You keep on absorbing more and more, but you emit less and less. Your temperature will just keep on blasting up. Right? Vice versa. If you have a bad emitter and a good emitter and a bad absorber, what happens? You keep on emitting more and more, you will cool down. So this Kirchhoff's law of radiation simply says a good absorber is also a good emitter, and vice versa. That means a black body is a pretty good emitter. Again, don't get confused. Black body does not reflect, but black body can absorb all that energy, make it its own, and then emit its own photons. That is always acceptable. So that means if you wear black clothes and go out into the sun, you get heated up pretty fast. But when you come into the room, you'll also cool down pretty fast. It's a good emitter and absorber. Clear? Great. Let's see a question based on this. Any doubt so far? Now, let's say a black body and a normal body of same dimensions. Are placed in a hot furnace. So furnace is like pretty high temperature. So the question is, who looks more bright? After a few seconds. After a few hours. Then what you did, after a few hours, then they're removed and placed in a cold room. So you kept it inside the furnace for a few hours and then you took them out. And they are removed from furnace. And placed in cold, dark room. Now who looks bright? So there are 4 questions. Again, after a few seconds and after a few hours. So first you kept it in a hot furnace, then you took them out after a few hours and kept them in a cold, dark room. Hope the question was clear. I think I'll give you a minute. This is how they'll play theoretical questions. Hmm. What do you guys think? Hmm. Normal, black, normal, black, normal, same. Now you need to understand when you say something is bright, Howard, why do you think something is bright? If more light comes from that area, you think it is bright, isn't it? Isn't that? If you have 2 bulbs, the bulb which emits more light or the more light comes from that particular area, I think it is more bright. Sun has something called black spots. So on sun ka surface, right, there are certain areas, where the temperature is due to high magnetic field, the temperature is around 1000 to 1500 degrees less. Again, when I say 1500 degrees less, the normal temperature is already 6000 degrees. Usme 1000 degrees less, matlab it is still damn hot. Right? So because of that thing, right, it looks like there are black spots on the sun. It's like sun has some pimples or something. Getting it? So it looks so because it's little cooler, so it looks like black. But the thing is that. So let's see what is happening here actually. So when you put them in a furnace, so furnace is pretty hot. When you put the black body in this and the normal body, so the black body is a good absorber, so it starts absorbing a lot of radiation. There is a normal body also absorbs, but little less. Now you tell me, if you absorb a lot of radiation from the surrounding, right, do you get more light to your eyes or less light to your eyes? If the black hole is absorbing all the light from that area, don't you get less light rays towards you? Then what do you think? Do you think it is bright? You will think it is actually dull, isn't it? Is that making sense? You think it is bright if you get more light rays. But this black body being a good absorber, it starts absorbing all the radiation from the surrounding. So it feels less light rays are coming. So black body actually looks dim. So the normal body is bright initially. So that is the meaning of few seconds. So we are assuming the body still didn't reach a steady state. So black body absorbs at a faster rate. Therefore, the surrounding becomes dim. So if 100 light rays are coming and if you're absorbing 70, I can see only 30. And the normal body absorbs only like 20 and I can see 80. Definitely, I think the normal body is more bright. So for the first answer, the normal body, this is after a few seconds. And eventually what will happen? After a long time, both will reach a steady state. What is steady state? Whatever you're absorbing, you're emitting the same amount. The black body is absorbing more, but it is emitting also the same. The normal is absorbing less, but it is also emitting the same. Now you tell me, if you absorb and emit the same thing, what will I think? I'll think they're same. Both will be same. And technically speaking, you can't even tell who is a black body and who is a normal body. They just get mixed up with the background. You're getting it? Because the background is also giving 100 light rays, the black body is also giving 100 light rays. You don't even notice the difference. You won't even think it is the same thing. So basically, after a long time, they reach a steady state. So black body is still absorbing more, but it is also emitting more. It's a good emitter. They reach steady state. So absorption becomes equal to emission. Now, when you put it in a cold room, what happens? Why would they emit same? No, they won't emit same. Whatever you absorb, you emit that same amount. Let's say black body is absorbing, let's say surrounding is giving 100. Black body is absorbing 80. It will emit 80. Surrounding is giving 100. Normal body is absorbing 20. Normal body will give 20. For you as a person, what will you think? You will think they're not absorbing anything, right? So black body is absorbing more than the normal body, but it is also emitting more than the normal body. Got it? So the emission and absorption of the body is same. They're not equal. So when you put them in a cold room, now what do you think will happen? The black body is pretty hot, isn't it? You kept it from a hot room and kept it in the room, so black body emits heat faster. So it will cool down faster. That means in return, it will also emit more radiations. So it will look bright. So the moment you immediately put it in the cold room for a few seconds, this will illuminate more. And eventually both will cool down, so they will look same. So black body, the final answer is same. Is this making sense? There we go. So when you leave for a few hours, it always reaches steady state. Once you reach steady state, you can't tell the difference. Main problem is always the few seconds part. Abhinav, focus on the class, right? You're busy with all other stuff. So this is our mini furnace. Did you see the starting part? Black body radiation starring Iron Ball, like Iron Man, and Hulk, like Brick Chunk, meaning Avengers types. So we have a mini furnace. So tomorrow, if you're taking metallurgical engineering and you want to melt something and stuff, you don't actually have a big furnace, you have a mini one. So that's your Iron Ball. That's your Brick Chunk. Now, can you tell me who is close to a black body? The Iron Ball or the Brick Chunk? Iron Ball. Metal is a good reflector, isn't it? Does a black body reflect? Isn't a metal surface a good reflector? So iron ball is actually a good reflector. The brick chunk is a black body. It's close to a black body. Are you getting it? So black bodies are bad reflectors. They don't reflect anything. So brick chunk is close to a black body. So when I take this and put them in a furnace, like this is a question, you can see what I expect. There. So you kept the ball and you kept the brick chunk. Did you notice something? You can see the background. It looks a little dim. Before putting that, can you see the background? When you don't put it, can you see the background? You can see, but it's too bright, isn't it? It's too bright because everything is coming onto you. Now see what happened when he kept both of them. Did you see something difference? The whole surrounding became dim. That is because these two things are absorbing so much radiation. Now it doesn't look as bright as before. This is what I was saying. So when you put the bodies that they absorb, the surrounding becomes dim. You keep it inside and close it for like a few minutes maybe. "30 minutes. Now can you see them? They reach the steady state. So क्या हो रहा है? They're still absorbing, but they're also emitting the same amount. So you can't even tell the difference. They almost get mixed up with the background. And if you see the brick chunk still looks a little blackish and dull, that's because of that. And this is what happens after a few hours. And when you reach steady state, they look same. They mix up with the furnace. So look at the comparison. After a few seconds when you keep and after a long time. Can you see? You can see the background. After a few 30 minutes, you can't see the background. This is what I was saying. So when you put a black body and a normal body in a furnace, they absorb so much light, the whole surrounding becomes dim. The black body will look more dim. Here, it's not that clear. Ansh, you're not able to see the screen? Others can see? Ansh, I think there are two screens, I guess. Something happened. Anyone who can't see? All can see? I think only Ansh, something happened with it. I'll post this video in the group anyways. Wait, I'll do one thing. Maybe I think while sharing that, I did something, I guess. Ansh, can you see now? No? Can see, na? So this is what I was saying, meaning if you missed everything, I'll just brief it up pretty fast. So there we have an iron ball and a brick chunk. This is the furnace. So when you keep them initially, can you see? They start absorbing. So surrounding is visible. दिख रहे पीछे background क्या है. But if you keep them inside for half an hour and then you remove them, this is how that looks. They mix up with the background because whatever they're absorbing, they're emitting. So the whole thing looks illuminated. So this was the difference he was showing there. See, initially when you kept them, did you see that since they're absorbing more, the brightness is less. Clear? Now tell me, if you take out from this furnace and keep it outside, who will cool down faster? The brick chunk or the metal block? Again, who is the close to black body? The brick chunk. So brick chunk should cool down much faster. Again, don't get confused. Huh? Iron ball is a good conductor. It has good conductivity. We are talking about radiation. Iron ball is a good conductor, no doubt about it. It has nothing to do with radiation. And now see here, they're taking out the iron ball. So first we kept the iron ball. Matlab, it has more time to emit heat. You can see how the color is changing from yellowish to red. Now you put in the brick chunk. Look at brick chunk, how fast it cools down. See, even though you took it after a few seconds, the brick chunk cools down much faster. Clear, everyone? There, that is one thing there. Yeah. So that is how they can frame questions on black body part. Next thing, let's go into little mathematical part. Stephen's law. We'll directly write on the formula there. So what Stephen's law says is dq by dt is minus sigma AET body power 4. A pretty rare formula, power 4. We have very few formulas with power force in physics. So here this dq by dt is the heat emitted per second in the form of radiation. That means if you have a body and let's say temperature of the body is TB, so the amount of energy it emits is power 4. This is experimentally derived. So it depends on the surface area, it depends on the nature of the material, it depends on the temperature. So here first let's see each term means the negative sign indicates the energy is lost. So when you're emitting radiation, you lose energy. dq by dt, rate of change of energy. So sigma is called Stephen's constant. It has a nice value to remember. 5, 6, 7, 8. 5, 6, 5, 1, 6, 7, 10 power minus 8. So the units are watt per meter square, Kelvin, power 4. A is the surface area. So that means if a body has more surface area, it emits more radiation. So you can see this thing during winters, right? The dogs just curl up and sleep. Ever seen them? Even when it is pretty cold, even you do that. We curl up and sleep. What you're trying to do is indirectly, they're trying to decrease the surface area. The lesser the surface area, lesser you emit, so you can maintain your temperature. You know, in Antarctica, the winters, right, temperature drops to almost minus 35 degrees. So all these female penguins, right, they go out for hunting during this harsh winters. They leave the egg with the male penguin and they go for hunting. And these male penguins are stuck there at minus 35 with the egg between that. If you have seen that Happy Feet movie, seen that? They actually have an egg between the two legs and they're just walking around. So how do they survive? So what these penguins do, right? They form a huddle. They form almost circular kind of things. So the penguins they huddle up. So when you huddle up, what will happen? You're decreasing the surface area and they do something interesting. Now, if you just stay like this, everyone will freeze to death. Eventually, the outer penguins outside will die. So what happens is the penguin on the outside will stay there for some time. Then it comes inside. This penguin goes outside. This goes inside. This comes outside. This goes inside. This comes outside. So it's like a conveyor belt. The penguins are continuously going in and out. They stay outside for some time. Then they go inside. So the penguins take turn one after another. So the penguins in the middle are warm. Penguins outside keep on getting cold. They get back inside. They go out. Like this, they survive for almost 2 months in that brutal minus 30 degrees winter. Then summer comes, the female penguins come back with some fish and all that stuff. Eggs are ready to hatch. Life goes on. So A is the surface area. TB is the temperature of the surface of the body. In Kelvin. E is the coefficient of emissivity. It's not restitution. Be careful. It's again basically the ratio of energy emitted. So basically it's a dimensionless. E ka value lies between 1 to 0 and E is equal to 1 for black body. So perfect emitter is E is equal to 1. Now here there's something important. This formula only tells you about the radiation emitted by the body. It doesn't tell you how much you're absorbing. And if you notice something, this does not depend on the surrounding temperature. So how much radiation you emit will depend only on your temperature. It doesn't depend on what is outside temperature. That means if I take a body at minus 100 degrees and put it in a 1000-degree furnace or put it in a 0-degree room, it still emits the same amount of radiation. It emits same amount, it absorbs differently. So radiation emitted is independent of the surrounding temperature. E0, it doesn't emit anything. It's an it doesn't absorb anything. E0 doesn't absorb, doesn't emit. I think then most of it will just get transmitted maybe or reflected. Is independent of the surrounding temperature. This is the kind of question they'll ask in advance, more than one choice. The radiation emitted by a body, right? It doesn't depend on what the surrounding temperature. Net will depend. But if I'm asking only how much are you giving, I don't care how much is the surrounding temperature. This completely experimental. You should know the formula, but this is not the complete formula. We will write down the full one, but this is the first part of it. How much you emit. Clear. Next thing, we have Prevost theory of heat exchange. Go ahead. Any doubt so far? So what this thing says is, if you have a body, and let's say temperature of the surrounding is Ts, so you start absorbing heat from the surrounding. So at any point of time, you're always absorbing and emitting. So dq by dt is plus because you're absorbing sigma a e t s power 4. This is heat per second absorbed from the surrounding in the form of radiation. And if you observe something here, this is independent of temperature of the body. Whether the temperature of the body is 0 or 1000, it will absorb the same amount from surrounding. So how much you absorb will depend on the surrounding. How much you emit will depend on your temperature. Net will depend on both of them. Now, if you combine these two, the final formula is this. This you should remember. dq by dt minus sigma a e t body power 4 minus t s power 4. There you can note down this one. So when you combine the Prevost theory and the Stephen's law, you get this. This would be the net heat per second. Absorption minus emission. So now if TB, if temperature of the body is greater than temperature of the surrounding, your emission is more than absorption. You'll cool down. So the sign remains negative. If temperature of the body is less than Ts, emission is less than absorption, your temperature rises. You'll absorb more than you emit. The sign takes care of it. So if someone asks you like this, if temperature of the body is minus 100 degrees, and placed in a 1000-degree furnace. So if someone asks you how much radiation are you giving out, that will depend on sigma A. So since it's at giving out, sigma A E, temperature must be in Kelvin 173 power 4. How much radiation are you absorbing per second? Sigma A E, temperature in Kelvin 1273 power 4. The net will be TB minus TP power 4 minus TS power 4. There, have a look at this. So in radiation, this is our first mathematical formula there. We only have two formulas in this, but most of the problems are based on this one thing. Copied? Let's see a question. E value depends on the nature of the materials. If we polish a surface really well, E value decreases. E is equal to 1 is a black body, right? So higher the value of E, you're closer to the black body. Let's see one question. So we have a body here, we have a body here. Radius is R, radius is 2R, E is equal to 1, E is equal to half. Temperature of the body is 127 degrees. Temperature of this body is 327 degrees. Temperature of the surrounding is 27 degrees. Find the ratio of net heat per second. Now remember, mains mein na, they won't say net heat and all, they'll simply say heat per second. So generally that specific thing they'll ask in advance, they'll specifically mention. So mains mein they don't think so much. So when they say heat per second, they're talking about net heat only. The word would be something like this: the radiation emitted by the body is what? Then understand he's only asking about emitted, not the total heat. But if we simply say heat, the net heat. The wordings have to be careful, because this is one thing that I noticed, the more precise we do here, suddenly mains may, you guys, instead of solving the question, you keep trying to, look at the terminology, you try to find words and, mistakes in their English. You won't have so much time in advance mains. So this means net heat. So keep that in mind. Meaning there is one of your senior who used to do this thing. Meaning, just listen to this thing. I used to scold him a lot. I mean, this guy was a little stupid also. Sometimes I feel that way. Question ये था. A disc is rotated and placed on a floor. Right? Find the time when it stops slipping. Okay, there's a question like that. A cylinder is taken of mass m and radius r. It is given omega and placed on a rough ground. After what time, find the final velocity. This was the question. How will you draw the diagram? When you say this thing, remember which part of this question is this? Conservation of angular momentum, remember? Think about it. The question is find the final velocity when it stops slipping. This is the word. So you take omega, then you solve angular momentum, blah, blah, blah. This guy comes and argues, why can't I take the cylinder like this? I will spin it like this omega and place it on a rough ground. Then he's not wrong. I'm getting it. He's not wrong. But I said, yeah, mains may they won't expect, like I told him, did they give you muka value? No. Right? You have no information and you want to solve this problem. He says, how do you know? Then I told him why it is like this. Why can't you take the cylinder like this then? ऐसा भी रख सकते हैं ना cylinder. I said, see, you also have to understand. Can you solve this question with the given data? No, you can't solve. So, and he said no slipping. Find the final velocity. He says that only. Sir, finally, if you keep like this, the thing will stop, na? So V is 0. And he said, okay, is that then the option? No, it is not in the option. So he says, how can they do that? They should give marks for that also, na? I said, yeah, abhi exam mein, you are thinking so much instead of solving. Whom are you going to go and argue with the examiner? So be careful with that. Don't fall into that trap. I'm not saying you're wrong. That kid was not wrong, but you'll waste 5-6 minutes unnecessarily on that and you lose. So you need to understand. Get this simple formula substitution. There's nothing there. Direct formula substitution. Let's see, just substitute. So dq1 by dt, sigma area is 4 pi r square, E ka value is 1, and temperature would be 127 plus 273, 400 power 4 minus 300 power 4 by sigma 4 pi to r whole square. This is half. This is 327. How much is this? 600 power 4 minus 300 power 4. Sigma will cancel, 4 pi r will cancel. This is 4 power 4 minus 3 power 4 by 2 into 6 power 4 minus 3 power 4. There, I will leave it to you. You can simplify this. So that can be written as 4 square minus 3 square. 4 square plus 3 square by 2 into 6 square minus 3 square and 6 square plus 3 square. That would be 25, 7, 2, 27, 45. Whatever is that. Clear with this? So there, I can leave the working to you. You can simplify that further. They do ask, huh? This was like a mains level question or a CET type question. They do ask. Sometimes they do get. Clear? Take a break. Come back with 7 to continue from here. Come back with 7-1. Any doubt so far? Okay, come back in 10 minutes. R option. Next one. So if you take sun, so sun is emitting radiations. So temperature of the surface of the sun is 6,000 Kelvin. Radius is almost 10 power 6 kilometers. For sun, we will take approximately is equal to 1, almost a black body, and the surrounding is vacuum. So when you say surrounding is vacuum, so surrounding has no temperature. Now you need to ask yourself, okay, sun is emitting energy, great, but who is giving energy? Like, where is this energy coming from? So what actually happens inside the sun? So sun emits radiation by converting mass into energy. By nuclear fusion. So recently, if you see last 3 days back, no news came China they were able to create a 100 million degree thing. Now creating high temperatures is fine. Many people did that, but the thing is sustaining it for hours, for few hours is a big deal. So basically, we are a little closer to nuclear fusion now. So for a nuclear fusion to happen, you need at least 10 lakh degrees temperature. 10 lakh. The biggest problem with that is creating is not a problem. After creating 10 lakh, where the hell are you going to keep this? There is no container which can withstand such kind of temperatures. So what we do is currently the model which we're using is a tokamak. It's actually a donut shape. So it's like a cylinder. It's like a donut shape. You can imagine a closed pipe. Something of this sort. It's like a cylinder there. So the logic is this: you generate such a high magnetic fields, right? That material which is at 1 million Kelvin is floating in the space. You can't touch any conductor. If you touch any material, you will destroy it. You have to make that material, that high temperature, float in space by repulsion due to high magnetic fields. And to generate such high magnetic fields, you need to use superconductors. And superconductors work at minus 192 degrees. Meaning, just look at the contradiction. You have the world's coldest temperatures and the highest temperatures at the same spot. You need very cold temperatures to maintain that superconductivity, and you need high temperatures for maintaining fusion. So people have done that. Korea was the first thing to do. They did create around 1 lakh degrees. The headache was maintaining it for long enough for the fusion to start. But I think China, they were able to maintain it for a few hours. That was a major breakthrough. So E is equal to mc square. This is the energy mass equivalence. And today morning also the news came that Indians also did something like that. They were able to create 20 times more hotter temperature than sun. But I think maybe they just did it for a few minutes or few seconds, so they're not publishing it yet. So let's see. It requires a lot of funding, right? That's the biggest deal. But this is the thing, next country, whoever makes the fusion reactors, they will be the next world superpower. And if we don't make nuclear fusion reactors, we as a humans will go extinct in another 100 years. That's for sure. So this is what happened. This is the equation which tells you how mass gets converted into energy. Einstein mass equivalence equation, pretty famous one. Just to give an example, what is the meaning of this thing? If you take 1 kg mass, so the energy it releases is 1. The C is 3 into 10 power 8 ka square. That's almost 9 into 10 power 16 joules. You know how big is this number? Means if you can actually take 1 kg mass and convert into energy, you can run the entire country, right, for a month. for a month. You can run the entire country, every train, every fan, every AC, every industry, every factory. You can run for a month. Just 1 kg mass. So in a nuclear bomb, what happens is around half kg to 1 kg mass gets converted into energy in a very short span. When you release this much energy in such a short span, it becomes hugely destructive. That's why nuclear weapons are so dangerous. If you see nuclear submarines, right, you need not refuel a nuclear submarine for 20 years. You know what is the how long can they travel? They can travel 1 lakh kilometers before refueling. So what stops a nuclear submarine, from sustaining is not the fuel, but the amount of food you have inside. They have pretty nice thing, if you have a nuclear submarine, you can do a lot of interesting things. You have a nuclear reactor, means you have a lot of infrared electricity, right? You can take the salt seawater, right? You can do electrolysis and you can create oxygen. So people inside will have enough oxygen to breathe. And you can make this salt water into fresh water, you have water to drink. So you can just stay in the submarine for months. As long as you have food, you can just stay there indefinitely. So that's why nuclear submarines are very powerful. What's stopping them is the food. So, anyways, getting back to the question. So the question is: so the sun is emitting energy by converting into this thing. Someone wants to go and catch the fish from the submarine. Maybe they didn't think about it, right? We will inform them. At a depth of 250 meters, you go out to catch fish, you will get crushed to death, right? Find the mass lost by the sun every second. So the sun is converting mass into energy and you're emitting in the form of radiation. So sun is losing mass. So how much mass is the sun losing every second? Get it? Others do keep your cams on. Let's see. 816 kgs ne both come here, Ansh. You messed up something. Let's see. So the idea is what? Did you convert that kilometers into meters? So dq by dt is sigma A E temperature of the sun to the power of 4. This is that energy that you're emitting every second. This must be, so if you take energy per second, is mass per second into c square. So sigma A E T power 4 is mass per second into c square. So mass per second will be 5.67 into 10 power minus 8. Area is 4 pi r square. R is 10 power 6 kilometers. So that is 10 power 9 ka square. E is 1. Temperature is 6000. That is 6 power 4 into 10 power 3 ka power 4. So 10 power 12. Denominator mein we have 9 into 10 power 16 c square is there. So this guy would be 5.674 pi. That is 6 square. 36 by 9. So that is one more 4. 10 power minus 8, 10 power 18, 10 power 12 by 10 power 16. This would be 4416, 5.67 pi into 16 into 36 into 10 power 6. That's 10 power 24 and 30. This is kgs per second. So this thing, if you round it off also, you'll get something around 10 power 8 kgs or something. That's almost like quite a big, almost 1 lakh tons, 1 lakh to 2 lakh tons. Burj Khalifa is 5 lakh tons. So literally you can say roughly around that much mass you're converting is per second, that much mass is going off. Sun has a huge mass. This is nothing. Sun ka mass is around 10 power 30. So don't worry, sun will not get extinguished anytime soon. We are safe. Clear with this? 1.3 into 10 power 10 it seems. So you guys check it out. I'll just believe Devansh. If it is wrong, you can scold them.
Wrong.
Idiot. Chalo, next one. I'll leave the calculation take. So we got a body here. Mass M, specific heat S, temperature T. Quotient of emissivity E, outside is vacuum. So what will happen? The body will start emitting radiation. That means it will cool down. Find the temperature at time T. Let's say initial temperature is T0. A solid sphere at temperature T cools down due to radiation. Find temperature at time T. Let's get this. You need radius. Yeah, take the radius to be r. Just try, my system just crashed. One thing is clear, temperature is changing, we have to integrate. So let's see the steps. So dq by dt is minus sigma AE temperature power 4. Surrounding is vacuum, so you don't consider any TS power 4. And dq is how much? ms dt. This comes from calorimetry. Shift it here. So dt by t power 4 sigma AE by ms d time. So be careful. Small t is time and capital T is temperature. Integrate this. This limits will be from t naught when time is 0. Time is small t. This is t. T power 4 integration is x power n. So that would be t power minus 3 by minus 3. Limits will go from t naught to t minus sigma AE time by ms. Shift everything that side. So we'll get 1 by t cube. 3 will go that side. Minus also will cancel. 1 by t naught cube plus 3 sigma AE time by ms. Clear, everyone? Here a minute, something happened with my internet. Mm, yeah, next thing. Everyone can hear me? Is this clear? Someone respond because I can't see you guys. Did the meeting close by any chance? Okay, all are there. Why is my system crashing? Okay, anyone there? Just unmute and say yes.
Yes, sir.
Yes.
Yes,
Okay.
yes.
Great. My PC, for some reason, it crashed again. Let's see. Keep trying. Let's see one more question. Hope this was clear. Then let's say we have a spaceship in the form of a cone. The base is made of an hypothetical material. which emits monochromatic wavelength. So what is the meaning of monochromatic? Single wavelength. Perpendicular to the surface. Now, normally when you take a surface, right, it emits radiation in all random directions. So we are making a big assumption here. The curved surfaces do not emit any radiation. Meaning, so we got a thing like this. So this is E0, E0, E is equal to 1. So this surface is emitting photons. Now remember, I told you in the beginning, photons also have momentum. So these photons, when they're coming out, right, if they have momentum, so they kind of behave like rocket propulsion. So now my PC is online. Just give me a sec. I don't know why it crashed. Okay. So this is emitting photons. So this photon, it kind of behaves like rocket propulsion. This is actually a concept by it. Actually, theoretically, it works, right? This is, NASA is also working on this thing. It's called a solar sail. So basically, by using the sun car radiation, you can propel stuff, just like it behaves like rocket propulsion. Let me write down this. Ships may have a wind ka sail. So how does that work? The wind comes and hits the sail, and because of that, the ships move. Similarly, in this thing, the idea was you can use this radiation from the sun and these photons. When they come and hit this thing, the thing moves forward. It does actually give a force, but the thing which is stopping us is not the concept, but the materials. You need to have a very thin material over a large area in order to get some appreciable amount of force. So that is what is stopping us. So this concept is called solar sail. You can check it out. After the, in the group also, I'll post a video on this. It has a lot of practical applications also. One of the application was in the future, let's say if some asteroid is coming towards the Earth for collision. So one of the idea was this: you can launch a solar sail, attach this thing to a solar sail here, and this thing can be dragged a bit away from the trajectory. So you can just drag it away from the Earth ka path. So it has some applications like that. So if this thing is acting like a rocket propulsion and the rocket is going forward, and there is a name for this also called radiation pressure. So when you switch on the light, it actually applies force on you. It's too small to feel it. And let the mass of the rocket be m, temperature is T. The radius of the base is R. So we have all the information. And surrounding is vacuum. And there is no gravity. This something like this will be an advanced paragraph question. Find the velocity of the rocket at time t. So if this is acting like a rocket propulsion, rocket will go forward. What will be the velocity after time t? But is the concept making sense? Currently, the kind of things we use are called ionic engines. In that, what they do, they use this uranium and everything radioactivity. It emits alpha particles. So alpha particles, when they go out, the rocket goes forward. So this is not the initial stages. Once the rocket reaches into the space, right, and then after it has finished all the fuel, and when the rocket is just, the satellite is just going away towards Pluto and out of the solar system, we have an ionic engine. So I think currently the fastest man-made object which is there, I forgot its name. It's traveling almost at a speed of 63,000 kilometers per hour. So that thing has an ionic engine. So they have a radioactive sample which is emitting photons continuously, and that keeps on adding the speed by little by little. But this is more revolutionary. This is the way we use the Sanka radiation which is coming and use it like a sail. Why you want to be a Viking, Ray? Solve this question. Why? What does Vikings have to do with this? Put it on. You can be a good fiction writer, Ray. How do we approach this question? You'll get these kind of things in advanced paragraph. They'll just ask you something completely out of the box, and there is one more thing. When they ask you something completely out of the, okay, you're saying the ship ka name is Viking. Okay, fine. I misunderstood. You should have said that, na? Or Voyager. Okay. I thought you wanted to be a Viking. Not a bad idea. You can send you to Europe or Denmark, and from there you can raid Britain and all, and loot. Interesting job profile. Viking, professional looter and destroyer of villages. How do we start? Think, I'll give a minute or two. Remember, I gave you two things. Energy of the photon is h by lambda, momentum of the photon is h by lambda. You'll need those. You'll need these two red boxes. Energy is hc by lambda, momentum is h by lambda. And h by m lambda. You didn't use sigma या t पर 4 रे पूर्वजा. बिना टेम्परेचर आ गया तेरा आंसर. And lambda तो दिया नहीं. No, lambda is not there in the information. Only that is you have photons. N is not given. N is the number of photons per second. You're there. You're close by. You need to convert that. This is one more thing that I noticed in advance, right? The more weirder the question, the more easy it is to solve. Again, don't get confused. I'm not saying question is easy. It is easy to solve. Means if you can figure out what the hell is happening, and the solving part will be actually easy. They won't try to make it complex. There's a tough question and there's a lengthy question. Look at this. So energy of the photon, I'll just write down, is hc by lambda. Momentum of the photon is h by lambda. Correct. So the power emitted by this So this guy is emitting energy per second, which is nothing but sigma AE T power 4. Now, how is this energy emitted? In the form of photons. So let the number of photons be n. Let n photons be emitted per second and wavelength lambda. Now, n is not given, lambda is not given. So then energy per second will be number of photons per second into energy of the photon is sigma AE T power 4. So this is n. Energy of the photon is hc by lambda sigma AE T power 4. So this is n into h by lambda is sigma AE T power 4. What is this thing then? This is nothing but total momentum per second. If h by lambda is momentum of one photon, if you multiply into n, you'll get total momentum per second. From Newton's second law, what is rate of change of momentum? Force. The force is nothing but dp by dt. So this is nothing but force. The force is sigma AE T power 4. You're done. Force is equal to mass into acceleration. So we get acceleration is sigma AE temperature power 4 by m. I forgot something somewhere. XCB here. And if you observe, this is constant. You have a constant acceleration. If acceleration is constant, I can use kinematics. V is equal to U plus AT. Therefore, speed is equal to sigma AE temperature power 4 into time by mc. That is your answer. It looks good, but once you actually realize the sigma is how much? 10 power minus 8. C is how much? 10 power 8 in the denominator. That is already giving you 10 power minus 16 in the numerator, isn't it? That is literally killing the entire value. So the force that you get will be very, very small. And then just to give a context, if I take temperature as even 1000 Kelvin, I'll still end up with some 10 power minus 6 or 10 power minus 7 value. This is the reason why it is not feasible. Theoretically, it does work. Have a look at this. So this is how you do. This is what I was saying. It is easy to solve, but you need to figure out, okay, this energy coming out is in the photons, and photons have momentum. I need to convert that into momentum per second and do all that stuff. Check it. It's a good one. Any doubts on this? Next one. Next one. This is also a good one. We'll start off with an easy one, then I'll make an advanced question also. Let's see a mains one first. So we have 3 parallel plates. A, B, and C. So 3 large parallel plates with a small distance between them. So basically you can treat them as infinite plates. The temperature of A and C is maintained at 2T naught and T naught. Meaning this guy ka temperature is 2T naught. C ka temperature is T naught. So these are maintained, meaning there's an external source which is maintaining the temperature. E is equal to 1 for all the plates. So now what is happening? A is emitting heat, C is emitting heat, B is also emitting heat. So heat is just flowing between them. So the question is, find the temperature of the middle plate, find temperature of B, and the heat flow between the plates. So how much heat is flowing from one plate to another, A to B and B to C, in steady state. Again, what is the meaning of steady state? In steady state, the net heat flow is zero. Means whatever is coming is going out. So temperatures have become constant. So eventually beaker temperature will become constant. What is the temperature and how much heat is flowing between the plates? Is the question clear, everyone? Why do we need infrared plates? If you take small plates, this is the problem. The radiation, some of it can go into space also, no? Everything will not fall on the other plate. So to avoid that problem, we made the plates very large. The diagram would have looked like this. These are like this, pretty huge plates. It's a very small distance. So they look like this, pretty close. So you can assume all the radiation is falling only on the plates. Get this? How will we do this? Anyone not clear with the question? We have three parallel plates. E is equal to 1 for all of them. A ka temperature is 2 T naught, C ka temperature is T naught. These are constant. You placed a plate in the middle, B. So now B will absorb some energy, reflect, some emit some energy, all that stuff. So finally, there is a steady state. Find the temperature of plate B and the heat flow between the plates. Think I'll give you 2 minutes. This is a good one. It's a good mains level question. Then we will extend this to an advanced level. Nee, I'm sure pretty close. I think you must have the calculation somewhere. Let me help you out. See. Think about in terms of energy. It's more easy to see that way. Now, whenever you have a plate and a temperature, what does it do? It emits radiations. Agreed. Now, what will this plate A do? It will emit radiation this way. How much? Sigma AE T A power 4. It will also emit this way. Sigma AE T power 4. So it will emit on both the sides. Wherever there is an area, radiation is coming out. So this radiation will go and fall on plate B. Now E is equal to 1, right? So what will happen? All the radiation will get absorbed. Agreed? Similarly, plate C also will emit sigma AE TC power 4. Sigma AE TC power 4. This also will go and fall on plate B, and B is a black body, so it will absorb everything. After absorbing, beaker temperature will start rising. Once beaker temperature starts rising, it will emit its own radiation. So B also won't keep quiet. It also will emit its own radiation. Sigma AE TB power 4. Sigma AE TB power 4. Because A and C are also black body, they also will absorb this. Now look at the whole story. So B is receiving this much energy, isn't it? It is emitting from A and C, and it is emitting this much energy. And if you're in steady state, whatever you are getting must be equal to whatever you're emitting out, isn't it? Does that make sense? So in steady state, heat given by A and C must be equal to heat emitted by B. So in steady state, heat received by B is equal to the heat emitted by B. So this will be, how much is it receiving? Sigma AE T A power 4, sigma AE TC power 4 is 2 times sigma AE TB power 4. Sigma AE will cancel, we get TB will be TA power 4 plus TC power 4 by 2 to the power of 1 by 4. So if you substitute here, this will turn out to be 17 by 2 to the power of 1 by 4 T naught. Check. Net heat transfer to be, yeah, it should be 0 na steady state mein. So whatever you're getting, you're emitting it out. Is this making sense, everyone? Now, if someone asks you what is the heat transfer between the plates, so we are talking about this thing. How much heat is flowing between the plates? Now, this is in steady state. So how much heat is going from plate A to B net? A is giving sigma A E T A power 4, and in return B is returning you back sigma A E T B power 4. This can be also written as sigma A E T B power 4 minus sigma A E T C power 4. Does that statement make sense? This is another way of doing the problem. Whatever heat is flowing from A to B must go from B to C also, no? Net heat flow. So if you solve this, you'll also get the same answer. This also works. So there are two ways to do. You can say heat received by B is equal to heat emitted by B, or you can say the transfer that is going from A to B must be equal to B to C. It's like they're in series, isn't it? Whatever is coming from A, that same thing must go through every section because it is in steady state. Is this making sense, everyone? So since I know TB ka value, I can substitute and finish it off. Any doubts on this page? This is important. Understand this, then let's make this a little more complex. Any doubts on this? Make sense? No. Now, an advanced problem would be something like this. There are n plates. This is the first plate, T1. This is the nth plate, Tn, meaning beach ka temperatures we don't know. So temperature of the T1 is the Tn is the temperature of the plates at the end. All are E is equal to 1. So exam, you know how they'll ask you? They'll say there are 100 plates. Find the temperature of the 40th plate and find the heat flow between the plates, something of that sort, right? T1 is greater than Tn. Find the heat flow per second. How much heat is flowing between the plates? Find heat per second. There are multiple ways of asking this, but let's start with this. Then I'll show you what else they can also ask you in steady state. So instead of putting one plate, now I kept n minus 2 plates. How much heat is flowing between the plates in steady state? See, the moment I use the word steady state means what? Whatever is coming in is going through. Do you guys remember this example I taught you in conduction? Mein? I'll show you. See, look at this thing here. Look at this thing here. 100 is coming in, 10 is going, 0 is there. It is not a steady state, na? Whatever is going is getting absorbed. Look at here. 100 is going, 100 is going, 100 is going. This is what I mean by steady state. If 100 comes in, 100 doesn't go, what will happen? यहाँ पे temperature constant नहीं होगा. This will increase. Is that making sense? So heat going from 1 to 2 must be equal to 2 to 3, 3 to 4, and so on. If it is not same, then the temperature of the plates won't remain constant. Now try. I'll give 2-3 minutes. It's a good one. If I ask you the advanced paragraph, I'll ask you this only. Find the heat flow between the plates and find the temperature of the 51st plate. Something of that sort. Think. Everyone should try. Just give it a try. Get some water and come. टेलीस्कोपिक फंक्शन तो आएगा, बट डिनोमिनेटर रॉन्ग है तेरा. I know. N is the power or divided by n ना वो. Whole by n, right? You're saying t power 4 minus tn power 4 का whole power 4, whole power n. नहीं, I'm not talking about that. I'm talking about n में इधर by n का बात कर रहा हूँ. Ahana, you also did the same mistake. I got what you wrote ना, that divided by n वो right नहीं है. Numerator is fine. Let's see. You guys did get it. You did a small mistake. Happens. See, look at it here. So let's say the heat flowing per second, this is h per second. So the same heat is flowing here, the same heat is going here, and so on. Now, let the temperatures be T2, T3, so on. Now, if you look at from here, this guy is giving out how much heat? Sigma A E T1 power 4. This goes in false here. In return, how much are you giving back? You are giving back sigma A E T2 power 4. Similarly, you're giving sigma A E T2 power 4. In return here, you are getting sigma A E T3 power 4. You can see what is happening there. Right, Anshahana. So if you look at the first plate, the heat flow between them will be sigma AE T1 power 4. This is the heat given by the first plate minus sigma AE T2 power 4. Be careful here. There is a vacuum. This is not T1 power 4 minus T surrounding power 4. समझ में आ रहा है? T2 surrounding नहीं है. T1 is plate and T2 is also plate. There is no vacuum here. There is no medium here. So don't think I'm writing sigma AE TB power 4 minus TS power 4. I'm not writing that. Now this must be equal to, this is the heat flow between the first and the second plate. Sigma AE T2 power 4 minus sigma AE T3 power 4. So on, if you continue this, you'll get sigma AA Tn minus 1 power 4 minus sigma AA Tn power 4. All these are equal. So any heat flow between two plates must be equal. So now if I get this equation, sigma AE T1 power 4 minus T2 power 4, this is equal to H. Sigma AE T2 power 4 minus T3 power 4 is also H. And so on. Sigma AE Tn minus 1 power 4 by Tn power 4. This is also H. If I add all of them, it's a telescopic function. You will see sigma AE. So this T2 will cancel, T2 will cancel, T3 will cancel, Tn will cancel. And remember how many H's are there? Be careful with the counting. Look at here. This starts with 1, 2, n minus 1. There is only n minus 1 gaps. Isn't it? If you have 3 plates, you have 2 gaps. If you have n plates, you have n minus 1 gaps. So this is sigma AE T1 power 4 minus Tn power 4 is n minus 1 into H. You're done. So therefore, the heat flow between them is sigma AE T1 power 4 minus Tn power 4 by n minus 1. It's a good result to remember. N is the number of plates. So this is a general result for n plates. The first one which I showed you is only for 3 plates. So there it was 3 minus 1. This is the heat that flows between 2 plates. So actually the more plates you keep between them, the lesser the heat will flow. They actually obstruct. Clear, everyone? So this is one thing they can directly ask you, how much heat is flowing between the plates. Another way of asking is, check out this page. Clear? So another way of asking, let me show an example. So they will say there are like 6 plates, 1, 2, 3, 4, 5, 6. Let's say this is 2 T naught. T6 is T naught. We want to find T4 ka temperature. So then this is what you can do. We know the heat flowing per second from 1 to 6, sigma AE T1 power 4 minus T6 power 4 by 6 minus 1 must be also equal to sigma AE T1 power 4 minus T power 4 by 4 minus 1. Does this make sense? Heat flowing from 1 to 6 must be equal to heat flowing from 1 to 4, na? Meaning what I did, I just removed these 2 plates and did again a problem. So this heat flow must be equal to this heat flow. So from here I can find T4. So this is how you can find temperature of any plate in the middle. You know the heat flow from 1 to n, and you can find the heat flow from 1 to any plate in the middle. So this is one way of asking a question. Find the temperature of the 51st plate. Another way of asking question, they will say initially there are 2 plates. And now let's say you kept one more plate in the middle. So let's say this was 2 T naught. This was T naught. This was 2 T naught. This was T naught. So here the heat flow is H1. By introducing a plate, the heat flow becomes H2. They can ask you find H1 by H2. So they'll say like this, there are 2 parallel plates and heat flow between them is 100 joules per second. When you introduce one more plate in the middle, what is the new heat flow? So here the value H1 will be sigma AE 2 T naught power 4 minus T naught power 4. If you see, the numerator will remain same. 2 plates are there, so 2 minus 1. H2 will be sigma AE 2 T naught power 4 minus T naught power 4. This is a 3 minus 1. So if you just divide H1 by H2, it's like 1:2. Or wait, I'll do one thing. Let's put 2 plates. That would be fun. So that would be 4 minus 1. So 1:3 ratio. Yeah. No, 3:1 ratio. So by introducing more plates, the heat flow actually gets obstructed. This is how they can ask questions. They can ask you how much is the heat flow between the plates, find the temperature of the middle plate, or what is the ratio of heat flow before and after introducing the plates. You get in the questions? So this is how they can frame an advanced paragraph question. So 3 plates is easy, but the moment I start putting 4 or 5 plates, suddenly things get little messed up. So have a look at this. It's a good problem. You should definitely check it out. So there's the variations you can get when you have a lot of parallel plates. Clear with this? Any doubts on this? You should definitely try this again on your own. Last one. Now remember there's one question we did and said temperature of the surface of the sun is 6,000 Kelvin. Who went and measured? The last known person or the god who went to the sun was Lord Hanuman. So after that, I think we don't have anyone who has visited it. So we don't have enough data actually. So how the hell did we find sun god temperature? Ever thought about it? Meaning, when I was in school, I used to have a lot of weird things like this. You ever heard this statement in biology? The average human blood is, average human being has a blood of 5.5 liters. So I used to think like, yeah, whom did you kill actually to measure this? Matlab, you won't kill a person, right? Just to bloody measure a value and put it in a book. So kuch to hoga. So we will see that actually using radiation you can find without killing him. But sun ka temperature, how the hell did we figure it out? So see, there is a way to do that by staying on Earth without going anywhere. So first we need for your information. First thing is defined as a solar constant. So solar constant is, it is simply the amount of energy received by Earth per second per unit time. Let's say per unit area, per unit time. So this you can just go out in the middle of the day and just put a small sample like a solar cell or something, and you can measure this. This value comes out to be 8.2 joule per minute centimeter square. You can convert this into SI units. So means if you take a 1 centimeter square area outside, every minute you'll get 8.2 joules of energy gets converted. You'll get this thing. So indirectly, this is nothing but intensity of the sun. Energy by time per area is intensity. If you convert this into SI units, this is 8.2 joules, minute is 60. This is 10 power minus 4 meter square second. So, okay, that's an SI unit there. This is one information we have. Second, during a solar eclipse, you can actually measure the sun ka angle subtended. Angle subtended by the sun. So if you take the sun here, Earth is pretty small. So if you take the diameter here and this angle is theta, the angle subtended by the sun theta is around 0.53 degrees. It's a pretty small value. This is the angle subtended by sun on Earth. So if you take the diameter of the sun and get this much information we have. That's it. Getting it? And take E is equal to 1 for sun. It's almost close to a black body. So using this information, we need to find temperature of the sun. And we actually found temperatures on something like this. Now, a little more info you need. Meaning, generally, when you say intensity is nothing but power by area. This thing I wrote already before. So, for example, if you take your sun here, if sun is emitting power at a distance smaller, so all this energy, right, is going in a spherical shell. So intensity would be power of the sun by 4 pi r square, where r is the distance from this point to that point. So intensity at a point is nothing but power emitted by the body. And how is this power going? The power is going in a three-dimensional shell, right? When you switch on a bulb, how does the light go? Light goes in all three directions, isn't it? So the light will pass through how much area? Surface area of the sphere, isn't it? Is that making sense? So the intensity is power by area. Which area? The area where the power is passing through. And area is passing through a shell. Surface area is 4 pi r square. So the farther you go, the lesser the intensity. It's 1 by r square function. This much information you have. So think, I'll give a minute or two and then I'll show you. You can find the temperature of the sun. Yeah, you will have some error, but still you'll get some decent number. We don't know the radius of the sun. We don't know the distance of the sun from the earth. Think. I'll give a minute more. see. So we have the sun. Earth is there, small. So the sun ka radiation is going onto the sphere. Let this distance be smaller. Let the radius be r and r. No, I don't know the radius of the sun. There are ways to find that also. We'll not get into that right now. R is the distance of sun from Earth. So from here, when you take this angle is theta by 2. This angle is theta by 2. Power of the sun is P, which is sigma A E T power 4. So intensity is power by area, which is actually nothing but solar constant. This is what we receive on Earth. So power is sigma A E T power 4 by 4 pi r square is equal to S. What is area? A is the surface area, which is 4 pi capital R square. P is 1. Temperature is power 4 by 4 pi r square. Now see, I don't know capital R, I don't know small r, but I know the angle. Now here we can see tan theta by 2 is r by small r. Now theta is very small, so you can approximate this to theta by 2. This guy becomes sigma r by r whole square is theta by 2 ka square T power 4 is equal to S. So therefore temperature will be 4S by sigma theta square whole to the power of 1 by 4. I know S ka value, I know sigma ka value, I know theta ka value. Just be careful, theta must be in radians. Theta is 0.53 degrees, so that is pi by 180 radians. S ka value I know everything. So if you substitute the values, this thing comes to around 5800 Kelvin. It comes pretty close to it with a small error, but there. Exam they will give you in variables only, 4s by sigma theta square and all. They won't expect you to solve it. But this is how you can solve. So basically the main idea is capital R and small r I can eliminate without angle. That becomes a savior. Clear? There. So we did see a lot of different things today. We saw sun is losing mass. We found the sun ka temperature. So there's a few things. So next class when we catch up on Thursday, we'll continue from here. We'll wrap up the chapter on Thursday. After this, we have we'll do maybe 1 or 2 more models on this. Then we will see something called Wien's displacement law, and then Newton's law of cooling is removed from the mains portion, but advanced may be here. So we will finish off that part also. So Thursday we'll wrap up the chapter. Okay, with that we'll wrap up for the day. Right, the test is still online, so Friday, so make sure to give it. So any doubts in today's class, anything else you can stay back and ask, also free to leave. So take care, stay safe. I'll see you on Thursday at 5:30.